So we've all done it, right? You sit at your keyboard, you type a question like, what is gravity into an AI, and then, boom, a perfectly articulated answer just streams across your screen in seconds. Honestly, it feels like magic. It really feels like the machine is sitting there pondering the nature of the universe and just thinking up a response. But, well, here is the absolutely fascinating truth. The machine doesn't think at all. It computes. It processes this massive amount of numbers through a highly structured, super rigid, and deeply mathematical architecture. So, in this explainer, we're actually going to tear right through that magic trick and look at the real, raw mechanics of AI.
Okay, let's just dive right into it. What we're dealing with is the complete 8-step inference pipeline. This is the literal journey your prompt takes through a large language model. And yeah, I know at first glance this probably looks like the wiring schematic for a nuclear submarine or something, but seriously, don't worry. We're going to demystify this whole complex architecture together. We'll track those 3 simple words, what is gravity, and follow them step by step through this exact pipeline until the AI spits out its final answer.
To make this super easy to follow, we've broken this explainer down into 4 logical phases: translating words into numbers, diving into the transformer engine room, predicting the next token, and finally, the speed tricks and output that make it all happen in real time.
All right, phase 1, translating words into numbers.
So before an AI can actually do anything, it has to convert our human language into a format it can process. And that all kicks off with the input and the tokenizer. You can kind of think of the tokenizer as a linguistic meat grinder. See, the AI cannot read the actual sentence, what is gravity? Instead, the tokenizer chops that input down into smaller, bite-sized chunks that we call tokens. What and is actually remain whole words, but gravity gets sliced into grav and itty. The tokenizer then assigns a unique numerical ID to each chunk. So what becomes 2601, is becomes 318, grav gets 26110. Bam, we have numbers, but, we aren't quite done yet.
Because actually, simply assigning a random number to a word doesn't magically tell the AI what that word actually means. That is exactly where the embedding layer steps in. This layer takes those raw token IDs and maps them into this massive, incredibly complex embedding matrix. Think of an embedding like a set of mathematical GPS coordinates. It takes a word and literally plots its true meaning, its context, and its relationship to other words inside a vast mathematical space. So words with similar meanings naturally end up with coordinates really close to each other.
And to truly wrap your head around the scale of what's happening here, just take a second to process this number. 4096. In a typical modern model, every single token is mapped into a 4096-dimensional vector space. I mean, just think about that for a second. We aren't just plotting a word on a flat 2D graph with an x and y-axis. We are literally giving each tiny, sliced-up chunk of a word 4,096 different mathematical properties just to define exactly what it means. It's honestly staggering.
Okay, moving right along to phase 2, the transformer engine room.
Now, before we look inside the absolute core of the model, we really need to understand how the AI operates over time. This is absolutely crucial. The AI actually has 2 totally distinct operational phases, the prefill phase and the decode phase. In the prefill phase, the AI processes all of your input tokens, like your entire prompt, in parallel, all at once. This relies heavily on raw computing power. But in the decode phase, which is when the AI is actually answering you, it is forced to generate just 1 token at a time. And in big models like GPT-4, this sequential loop passes through around 96 distinct layers. So this phase becomes incredibly dependent on memory. Basically, the AI reads your whole prompt at once, but it has to write its answer out sequentially.
Right, so inside the transformer block itself, we find what's called multi-head self-attention. This right here is the magic ingredient. This is what allows the AI to understand the context of your sentence. It uses 3 matrices, Q, K, and V, which stand for queries, keys, and values. The model is basically asking mathematical questions about how each word relates to every single other word in the sentence. It compares those queries and keys to calculate attention scores, which is how it figures out that the word gravity is the most important subject of the word what.
And this brilliantly illustrates the need for something called the KV cache. Because the decode phase generates words one by one, it would be just ridiculously inefficient to recalculate those attention scores for the entire sentence every single time a new word pops out. So instead, the model stores the previous key and value pairs in the KV cache. It saves a massive amount of computing power, but there is a catch. The KV cache grows linearly with the length of the text, and it eventually becomes the main bottleneck for the system's memory. which, by the way, is exactly why your AI chat might suddenly start slowing down during a really long extended conversation.
Oh, and once a token passes through that self-attention mechanism, it still isn't done. Not by a long shot. It has to run a veritable gauntlet. First, it passes through an add and layer norm to stabilize the data. Then it dives into a super complex feed-forward network that applies intense nonlinear math using some really funky-sounding functions like ReLU or SWIGLU before finally hitting yet another stabilization layer. And remember, this insane mathematical density is happening to every single token inside every single block up to 96 times.
Phew, all right, phase 3, predicting the next token. Having somehow survived the engine room, we finally reached the climax of the math. This is the exact moment where the AI actually makes a decision about what word comes next in its answer. And no, the model doesn't just guess out of thin air. The linear layer, also known as the LM head, maps all that processed data back against the model's entire vocabulary. And a typical vocabulary size for these massive models, it's about 128,000 tokens. That means, for every single step, the model has to evaluate 128,000 distinct possibilities for what the next fraction of a word should be.
To pull this off, the model uses a function called softmax. Honestly, you can visualize the softmax layer as just a giant 128,000 horse race. Softmax takes the raw output scores from the LM head and converts them into a clean probability distribution. It calculates the exact mathematical probability of every single word winning the race. Generally, most words have a probability hovering right near zero, but a few lucky candidates will spike, showing they are highly likely to be the correct next piece of the puzzle.
So how exactly does it choose the winner? Well, that happens in the sampling strategy. If the model is using greedy sampling, it simply picks the absolute highest mathematical probability every single time. It's entirely deterministic, meaning it'll always give you the exact same, highly predictable answer. But let's say you want the AI to write a poem, or maybe brainstorm some wild startup ideas. In that case, you turn up a setting called temperature. As temperature approaches 1, the model literally flattens out that probability curve, which allows it to occasionally pick the second, third, or maybe fourth most likely word. It basically injects a dose of creative randomness right into the output.
But of course, we can't let the AI be too random, or it'll just start speaking absolute gibberish. That's why we use guardrails, specifically top K and top P. Think of top K and top P like the bumpers on a bowling alley lane. They keep the AI from wildly hallucinating straight into the gutters while still letting it be pretty creative. Top K tells the model to only ever sample from a set number of the highest ranking tokens, say just the top 50. Meanwhile, top P, which is sometimes called nucleus sampling, tells the model to gather up the most likely tokens until their combined probabilities hit a certain threshold and then just discard everything else.
Which brings us to our final stop, phase 4, speed tricks and output.
So, you might be wondering, if this unimaginably intense math is happening thousands of times a second across hundreds of layers, how on earth does the AI type back to us almost instantly? Well, the secret lies in a few brilliant under-the-hood structural optimizations. The first is quantization. By reducing the precision of the weights from heavy, high-end floats down to INT8 or INT4 integers, engineers can drastically reduce the memory required by like 2 to 4 times. The second trick is flash attention, which effectively fuses all those complex attention operations together at the hardware level, massively reducing the amount of times the system actually has to read from its high-bandwidth memory.
But I gotta say, the absolute coolest speed trick of all is speculative decoding. See, because the main large target model is so heavy and slow, they use a tiny, blazing fast draft model to guess the next few words ahead of time. So the draft model might speed ahead and guess gravity is a. Then the massive target model verifies all of those guesses in parallel. It looks at the sequence and essentially says, yep, grav and idia are correct, accept them. But no, isa is wrong, reject those. The big model then steps in to generate the correct next token. It saves a huge amount of time by basically just checking the draft model's homework rather than doing all the writing itself.
And finally, we've reached the detokenizer. We've run through the entire pipeline, and the model has successfully spat out a winning token ID. Let's just say, for example, the ID is 17,042. The detokenizer takes that and flips that mathematical ID right back into a human word. Boom! 17,042 translates to the word fundamental. The AI has successfully added one more piece to its sentence.
And honestly, this brings us to the big epiphany of this entire explainer, generating one token at a time.
This colossal, mind-bending 8-step pipeline we just went through, with its 4,096 dimensions, 96 transformer layers, and 128,000 probability calculations, it literally runs from scratch just to spit out a single fragment of a word. And then it loops back, adds that new word to your prompt, and runs the entire gauntlet all over again just to find the next word. Over and over and over again.
When you truly understand the sheer mechanical reality of what's happening under the hood here, the fact that these models work at all, let alone in real time, is an absolutely staggering feat of human engineering. But it does leave us with a pretty provocative final thought. With millions upon millions of dense mathematical operations required to generate just a single word, what happens next? As we demand AI models that are orders of magnitude smarter and larger than what we have today, how on earth will our physical hardware keep up with the math? Thanks for exploring the inference pipeline with me today. Hopefully, the next time you type a prompt, you'll see the numbers beneath the words.